All right, let's work on the group work here. Encourage you to work with somebody else, but definitely can do this alone, right? All right, so this kind of will cover a lot of things in 5.2, just to kind of get us to the point where we then can get into the other part of 5.2 that we want to get into. All right, so here we go. Number one, table below is probability model for the number of cars in a randomly selected household, United States. All right, so part A, what is the probability of random selected household has 3 cars? We are literally looking for what is the missing value. Now remember that this whole thing has to equal to 1 or 100% to be a legitimate probability table. So we're gonna take 0.07 plus 0.19 plus 0.47 plus 0.06 plus 0.02. That's equal to 0.81. So obviously what's missing is probability that somebody has 3 cars is equal to 0.81. It's got a, whoa, no, sorry. That is what it's all equal to right now. So 0.19, that will be the one that is missing. Okay, easy enough because it's got to add up to 1 or 100%. What's probability a random selected household has at least 2 cars? So check this out visually. At least 2 cars means 2 or 3 or 4 or 5 or more. All right. So remember we said when we use the term or, I want you to think of addition. Right? So that's what I want you to think of. So addition rule. 0.47 plus 0.19 plus 0.06 plus 0.02, right? So that's the probability of X being at least 2 cars, greater than or equal to 2 cars. So 0.47 plus 0.19 plus 0.06 plus 0.02. So that's going to be 0.74, all right? Or 74% if we needed to change it to a percent. So that's one way to do it. The other way to do it is we could have added 0.07 and 0.19, which is 0.26, and complement it, or take it away from 1. We're still going to get the same answer, all right? So make sure you got those answers down and you can read that. All right, let's move on to the next piece here, which is doing a Venn diagram. All right, let's try this. And if you need to, right, you can kind of pause it, try it, and then check, see if we got the same answers. All right, 60 customers were served over the course of the evening. 52 customers ordered pizza, 16 ordered buffalo wings, 12 these customers ordered both pizza and wings. So this is important to us, pizza and wings, because that is the overlap. Those are the people who are doing both things at the same time, right? So now when we talk about mutually exclusive, are these mutually exclusive? Nah, they're not, because we do have people that have both pizza and wings at the same time. All right, so suppose we select a customer from the last Saturday at random. All right, so we're going to do this real quick, pizza and wings. So since I know that there is overlap between pizza and wings, I would literally overlap these, okay? So always start with the overlap people. Well, that's 12. There's 12 people that did both. All right, so now let's define 52 customers ordered pizza. So I'm going to put a 40 here. And remember, just like the last one, why am I doing that? Is because pizza should be 52 total. And 40 happen to be just pizza people, but 12 did pizza and wings, right? So that's what that one ends up looking like right there. Okay, now let's look at the wings. 16 ordered wings. Right, so I'm going to put a 4 here. Why am I going to do that? Remember, because wings together needs to add to 16. All right, so then we can start to define how many people are left over. 40 plus 12, 52 plus 4 is 56. So guess what? We got 4 people out here outside of pizza, outside of wings. Right? It is just those people there that didn't do either. All right? So there it is. And actually, that actually does part B, and you got to kind of flip to the other side. Sorry about that. What is the probability that a randomly chosen customer did not order wings or pizza? So remember, this is pizza or wings. So these 4 people did not, right? And then, you know, appropriate calculations. Well, I'm just going to go right back to my Venn diagram and tell you exactly what it is. All right? So there it is, okay? All right, let's move on to the next one. Here we go. Now we get to really dive into our addition rule and try to do that. Okay, list 2 mutually exclusive events for this chance process. Now we got events: bachelor's degree, master's degree, professional, and doctoral, right? Those are events. But we also have events called female and male, right? Those are all the different types of events that we have. So 2 mutually exclusive, which means they can't happen at the same time. So I would pick like, oh, I don't know, bachelor's degree and a professional degree. You can't get them both at the same time, right? So those would be mutually exclusive. Or maybe we go being female or being male. You can't be both at the same time. Right? Those would be mutually exclusive, right? So anytime that they don't have overlap, right, they could be considered mutually exclusive. So those would be my answers. I'm not going to write them all down because there's plenty of them to choose from, but many to do. What's the probability the person earned a master's degree? So here we go. Let's try notation. Probability, master's degree equals. All right, here we go. Let's look at master's degree. That's these cats here. So I'm going to go 365 total master's degree out of 1626 total people involved here, right? And then we could obviously calculate that. So let's go 365 divided by 1626. So I'm going to go with the answer of 0.2245. I don't know, something like that. And then we could turn it to a percent if needed to or want to. What is the probability a person selected to earn a professional or doctoral degree? Or meaning add. I always want us to know or means add. Professional degree or a doctoral degree, right? So professional, well, there's 74 of the 1626. Plus doctoral, well, there's 42 of the 1626. Minus, because you always got to minus the overlap. Do these 2 overlap? Nope. That means they're mutually exclusive because I put a 0 at the end. So therefore, 74 plus 42, that looks like we're going to get 116 out of 1626. And if we want to turn it to a decimal, which typically we do, 0.07 or 7%. Or means add. Okay, here we go. What's the probability the person selected is female or earned a master's degree? Probability female or earned a master's degree. So probability being female, that's 856 out of the 1626 plus earned a master's degree. That's these people. That's 365 out of the 1626. Now, I got to subtract off any overlap. Did I double count any of these people? Well, here's what you do. Female, masters. Do you see any overlap? I sure do. These 194. So subtract 194 of 1626. And that's going to give us our answer. So 856 plus 365 minus 194. Right, that's going to give us 1027 over 1626. And if I divide that by 1626, I get 0.63 or 63%. 63% chance that you would select either a female or somebody who got a master's degree. So that's what that looks like right there, right? A little bit of practice of doing some basic probability, doing some addition rule, thinking about mutually exclusive, and sometimes thinking about complement. Okay? So those are the things that we want to tie all together for 5.2.